Hi, I'm Ninad, and today I'm going to dive into neural networks from first principles. So, from ChatGPT to AlphaGo to self-driving cars like Tesla, the core mechanism behind them is neural network, or we call it a neuron, as we draw inspiration from the biological neuron. Now, why I'm doing this is because being a data scientist for almost I think 1.5 years, I have been diving into some research papers from Bengio's first paper from that is a neural probabilistic language model to Mikolov's RNN paper to attention is all you need paper. And I have been doing some tweaks and understanding what was the limitation of MLP, that is the Myrtle layer perceptron. And then I went to RNN and then saw it was generalizing better, but it has some problem like vanishing gradients. Then I used LSTMs, then GRUs, which is much simpler version of LSTMs. And then I went to the transform architecture and I understood why is it very important. And the code is on the GitHub, you can watch it. But I wanted to explain it for two main reasons. First is to solidify my understanding because I feel when we explain it is better. And second is just to spread the word. Again, I'm not an expert, I'm just a beginner in this field, but I have been, understanding from Andrej Karpathy and then reading papers, and it's fun. So let's get started. So what is a neural network from first principles? So it's nothing but a simple mathematical expression that takes some input and produces output. As simple as that. Okay, now these inputs can be of two forms. First is weights, some parameters like weights, and input like inputs. And they produce a value or output. And this is how it looks like. There are some inputs, which is weight or inputs, and then they produce an output. Now, before producing the output, we also basically take this and we put it in a function like tan h or sigmoid function of that nature. And the main reason for that is to squash the values. Now, if you see the tan h graph, it looks something like this. This is 1, this is minus 1, this is 0. If you put all the values, it will squash it to 1 and minus 1. That is the main purpose. Yeah, and that's how an output is produced. Now, in order for a neural network or this mathematical expression to produce the output that we want, we need three things. First is loss function. I'll also explain you these three things in very simple manner, don't worry. Second is gradient, or we also call it derivative in mathematics, or slope. And the third is backpropagation or learning. I'll explain you these three things, don't worry. Now first, let me show you how a very simple neural network looks like. So for some reasons, I will just explain you in very simple terms. So let's say there is this neural network or a mathematical expression that is z is equal to w1 x1 plus w2 x2 plus b. The b is the bias, these are the weights as I told, and these are the weights. x1 and x2 is the input, b is the bias, and z is the output of this network. Cool. Now we will create something called as loss function out of this. Now what do you mean by loss function is it tells you it's a different expression that tells you how wrong is this network performing as of now. Cool. In very simple term, it tells you how wrong is the network. Cool. Now, as you can see, this is our expression. Now, mathematically, let's say if z actual is 25, for an example, and this is z prediction. Now we have to see how far is this z prediction from 25. If it's 200, the loss will be high. If it's near 25, the loss will be less. And for these terms, to see how far is the value, we calculate something called as MSE, mean square error. That is, I think the formula for that is z actual minus z prediction square of this, and we divide it by the number of observation, that is 2 in our case. So this is a loss for our case, and we got the loss. This is the first stick. Second step for running a neural network or understanding a neural network is gradient, derivative, or slope. Now you can understand gradient or derivative from rate of change of anything based on a particular parameter. Now you must have seen that in high school we calculate the derivative. There are like particular formulas for it. If let's say this is a particular equation minus 4x plus 5, and now if I'm calculating derivative of y based on x, so dy by dx becomes 6x minus 4. This is the derivative. Now this tells us how is the value of x affecting the value of y. So this is the slope of this equation, or dy by dx, or gradient, or slope, or the rate of change. These are the similar terms. And now why this is important? Because it tells us how particular inputs are contributing to the loss function. How is input contributing to loss. As simple as that. And the last, the most important, is backpropagational learning. Now, this is a very simple mathematical equation, but it can be of any arbitrary input and it can be pretty complex. So, what backpropagational learning method is, we basically go deeper into the network, we see all the inputs, and then we update the value based on the gradient to make the loss less. As simple as that. We know a particular loss, that how wrong is the network. We know how much is every input contributing to the loss. Now, what we do is we modify these inputs based on the gradient to reduce the loss, which will help us attain a value that is 25. This is what backpropagational learning means. Go deep and update based on gradient. This is what are the three fundamental steps of making a neural network work. So keep that in mind. Okay, so now this is our loss. Now I will dive into the code. We will we will calculate the loss, which is already done. The first step is done, loss is calculated. The second step was basically calculating the gradient. Now gradient is calculated, as I told you, it is a value of how a particular input contributes to the loss. So we'll calculate the derivative of each input that we have based on the loss. As simple as that. So how it can be done is, now I want to calculate, this is what I want to calculate. Sorry, not derivative of loss based on dx1 and derivative of loss. These are the two inputs we have. If we know these values, we can update these values for the loss to come down. Now I will dive into the code and explain you how this system works, and so that you can have an understanding of loss, gradient, and backpropagation. And by the end of this lecture, you'll know how a neural network predicts a particular value based on the equation. Cool. Just one final thing before ending this lecture is, now this is one neuron, as I explained you. Now, as I told you, we will in the next lecture we'll discuss about the first paper, neural probabilistic language model, and then how were the language models, and then we'll talk about bigram models. Oh, wait, I won't confuse you for now. I'll keep that in the next lecture. But just for your understanding, we don't just use a single neuron for a network. We have a complete network. So we just don't use a single neuron. What we do is we use 2, 3, 4, n number of neurons in a particular layer. We call this as a layer. And this multiple layers is what is called as MLP, or multi-layer perceptron. And in the next lecture, we'll go deep into the Bengio's very famous paper, A Neural Probabilistic Language Model, and I'll explain you how this simple mathematical expression can predict names, Indian names of like really novel names like that has not been seen before. Hi, so let's get started. So as in the lecture, I told you about three important things for a neural network to work. That is loss, second is slope, and third is learning or backpropagation. So I just wanted to show you everything in terms of code now. So this is the equation that I just showed to you guys, and these are the weights, and this is the forward pass, and this is the loss calculation, that is mean square error, and these is basically what we call as gradient or slope calculation. Now what this is, it's basically chain rule in calculus, because we need to calculate the derivative of loss with respect to the variables, that is x1. So we cannot do it directly because it's not directly dependent, as you can see. So what we do is we basically use the chain rule for that. That is, we first calculate this, and then we calculate dy by w1, and then we sort of multiply. This is basically simple calculus. I hope you guys know it. So it's really simple. And once this happens, we know the slope values, and then we just update the weights. So these are the three steps which I told you. Loss calculation is the first step. Second is calculating the slope, and third is updating the weight. Now let me run this code and okay. I'm sorry, yeah. Let me run the code and yeah. So prediction was 1.6 when we just randomly put the value, we just put these values, and the true value is 25, which we want, and the loss is used because you can see it's like really far, and the gradients, these are gradient values, and then we update the weights accordingly. Now what we'll do is we'll basically do these steps in neural network. We'll see a forward pass, and we'll do the slope calculation, we'll update the weight, and then we'll keep doing it, and then we'll print the loss so that we can see like how the loss changes. So if I run it, so when there are 20 steps, this is for loop is running for like 200 steps, and for first 20 you can see the prediction is 17 and this is like 26. So these are the weight values and the loss is huge. And as the prediction increases and keeps going near to 25, the loss decreases, as you can see. So this is a very simple neural network. I hope you got the intuition of how a neural network works. And I'll be also attaching with this is my GitHub where I have basically implemented some of the foundational papers that I just talked about, from Benjio's neural probabilistic language model to Mikolos RNN, and then Graves till the Vaswani's attention is all you need paper. And so I'll just talk about how this different architectures work and what tweaks I did, what did I observe, and why was the transform architecture really, preferred, and why it was really good. So I have just updated the code, and if I just wanted to show you guys the papers as well. So this is like the first paper. I think this came around 2003. This is neurolinguistic language model, and this is the first paper when NLP was really properly used for language modeling or prediction of the words. And I have implemented this paper as well. So this is the architecture. You can see this is the lookup table, and then we squash it. This part we did not do, and then we use softmax. Softmax is basically where you take the logits and you calculate the probabilities. Now again, I don't want to go in detail. And here also you calculate the loss. I think you can see, yeah, this is the maximum log like Liverpool. So this is the kind of loss you use in language models. This is the number of features. That is how how you put in a dimension. And this paper talks about the fighting the curse of dimensionality. So this comes from again from a diagram model. So as we scale the diagram model, there are a lot of problems that occur because there are a lot of possible combinations that are coming in. So this paper fights that curse. And after that we go to the RNN paper. So RNNs were discovered like really early in the 90s, but it was not properly used by this paper. I think this paper was in 2010. Yes, 2010. And so RNN is like neural network, but there's something new to it. That is, as you can see, this input, there's some layers and this output. But with this some layers, there is another layer which is like context or the past information that you get. And this is sort of like improving the Benjio's paper. You can see like what problem it fixed. So Benjio had like fixed length context problem that we'll discuss. And yeah, so this is the squashing function, that is sigmoid activation they're using here. In the last paper they used TANH, and then these are some of the models they're using. And I think they're using hybrid model here. So yeah, this is the RNN, and RNN really generalized better, but there were some problems with RNN which we'll find out in this paper of Alex Graves from University of Toronto. And there were, RNNs are really great with generalization, but if there's some issue with the output, it sort of takes the past as input. So if it does a mistake, it's really difficult for it to recover from it. So I think it's addressed somewhere in this paragraph. And he will talk something about LSTMs in this paper, long short-term memory, and they have so basically it knows what to remember from the past information, what to forget from the past information. And then yeah, and he basically uses handwriting modeling as well. So this is something which is really interesting if you guys want to see it. And then we basically go to the on the neural properties of the NMTs, encoder decoder approaches. Encoder is basically where you take the language, we put it to some vector encodings, and then decoder is basically take this encodings and convert it to natural language. So we'll talk about GRUs in this paper and why GRUs are much more easier. So I think here it's discussed about GRUs. Gating units called as So this is, think of it as GRUs as simple version of LSTMs. That's what I can tell. And then finally we see the attention is all you need paper, where we talk about self-attention. And how does self-attention work and how it solves the problem of the context, and how does it remember everything and how it gets the context. Because see, here we were basically getting limited by the amount of information you would know, because as the network deepened in RNN LSTMs, it was really complicated, and RNN had vanishing grading problem which LSTM solved, and how did attention is all you need paper solved everything, and why is it such a widely used architecture. So we'll go into this, and if we get time, we also discuss about ImageNet and how did this paper is from Elias Utskov, Joffrey, and Alex. This was for CNN, and earlier both the architects were a little bit different. CNN was basically like parallel operations, but everything got converged into attention is all you need paper. And so we'll discuss about this. And I have also written down code for a transform architecture that I wrote, similar to this, similar to ChatGPT. Obviously not scaled up to that much, but a simple GPT. And I'll put all this code in the GitHub, and hope you love it. So thank you.